Dear students, a warm welcome to all of you for this video session. In this session, we are going to analyze the three-phase balanced delta connected loads. In the previous two videos, we have discussed some of the basics about three-phase circuits. I request all of you to watch those two videos for better understanding of this video session. What kind of analysis are we going to do in this session? So finding the phase currents and line currents drawn by the three-phase loads from the supply, and then finding the power drawn or power absorbed by the loads, and finally the finding power factor of the load. So these are the things we are going to find, and we call this as analysis of three-phase loads. Let us consider a three-phase balanced delta connected load. So already we discussed what is delta connected load. So three loads are connected in the form of delta, and it is connected to a balanced three-phase system. So a three-phase balanced system is supplying power to this delta connected load, and here the load is represented by Z at an angle phi. It means that Z is the impedance of the load connected to this particular phase, and phi represents the angle between the voltage across this phase and the current flowing through this phase. For example, let us take the voltage across this phase is VRY. This phase is connected to R phase and then Y phase. Therefore, voltage across this phase is VRY, and the current flowing through this phase is IR. Hence, this phi represents the angle between VRY and IR. Let us see this relationship with the help of this waveform. For simplicity, I have shown only one voltage and current. Since the loads are inductive in nature, the current will be lagging behind this voltage. That is, the starting point of the current will be lagging behind this voltage, respective voltages, by an angle phi. So this is what Z at an angle phi represents. Now the phase sequence we consider here is RYB. That is, VRY voltage starts first, VYB comes next, and then VBR. Already we discussed what is phase sequence. So the order in which the three line voltages are starting from the 0. And here, since the load is delta connected, the supply line voltage will be equal to the load phase voltage. Let us see the current flow in a three-phase system. Usually in a single-phase system, the current will be positive for 10 milliseconds and negative for another 10 milliseconds. Here in a three-phase system, you can see the direction of current flow. See, you see this R phase alone, the current is flowing back and forth. That is positive and negative. For more understanding, you consider, see this, for some time the current flowing through R phase is incoming, and the current is leaving through the other two phases, yellow and blue. At any time, one of the phase will be taking the current in, the other two phases will be leaving the current, and after some time the current may be entering through two phases, and that the total current will be leaving through one phase. This is the current flow in a three-phase system. Now we can see the current is entering through yellow phase and leaving through red phase and blue phase. Now again, after some time, the current will be entering through yellow phase and blue phase, and the total current will be leaving through red phase. So this is how the current flow happens in a three-phase system. but for simplicity and analysis purpose, we will consider all the currents to be going out of the nodes. Once again, consider this delta connected load and let us find the phase and line currents. That is what analysis. So the source voltages are given by VRY is equal to V at an angle 0 and VYB will be 120 degree. Later it will start, therefore V at an angle minus 120, and VBR is V at an angle minus 240. So the balanced supply means all the voltages will have same magnitude and they are displaced by 120 degree from each other. So the current flowing through each phase. So let us consider R phase. So what is the current here? IR. So current, we know that the formula for current is V by Z. So what is the voltage across this phase? It is VRY, because it is connected to R phase and Y phase. And what is the impedance of this phase? Is it at an angle phi? Therefore IR is equal to V at an angle 0 divided by Z at an angle phi, and if you take this phi to the numerator, it will become minus phi. Similarly, you can write for IY and IB. So these are the phase currents in the three-phase delta connected load. Therefore, from this again we need to find the line currents I1, I2 and I3. We know that in a delta connected system, line currents and phase currents are not same. So therefore, if there are three junctions in this delta, junction 1, junction 2 and this is junction 3, and if you apply Kirchhoff's current law at junction 1, you can see I1 is the current that is flowing outwards and IB also going outwards, and IR is going towards the node. Therefore, as per Kirchhoff's current law, incoming current is equal to outgoing current. So IR is the incoming current and I1 and IB are going away. Therefore, you can add them. Similarly, if you apply Kirchhoff's current law at the other two junctions, you will get IY and IB. So from this, already we found IR, IY, IB. Hence, it is easy to find I1, I2, I3 because they are the line currents. So we can just rearrange. I1 is IR minus IB, I2 is IY minus IR, and I3 is IB minus IY. So please remember these three formulas, I1, I2 and I3. So let us explain this process or analysis with the help of a vector diagram. Let us take the VRY, line voltage, as a reference vector, and we know that the other two voltages VYB and VBR will be 120 degree apart from each other. So this is the these are the three vectors, and always we assume that a vector diagram, keeping this as a center, it is rotating in anti-clockwise direction like this. Now we will represent the respective currents or the phase currents. So IR is the current flowing through R phase, and that will be lagging behind the respective line voltage by an angle of phi. Similarly, IY will be lagging behind VYB by phi, and also IB, IR, IY, IB are lagging behind their respective line voltages by phi. Now we have already written three equations. So let us take one. The line current I1 is equal to IR minus IB. So we need two vectors. One is IR and the other one is minus IB. So I1 is the vector sum of IR and minus IB. Here we have got IR, but where is minus IB? Let us draw the opposite vectors of these three. And as per the parallelogram law of forces, the resultant vector is this much, root of IR square plus IB square plus 2 IR IB cos 60. So the angle between IR and IB will be IR and minus IB will be 60 degree. We will see that. And further, if you simplify, cos 60 will be, or here, since it is a balanced load, all the phase currents are equal in magnitude. Therefore, commonly I will call this as a phase current, I phase. Therefore, further simplification, you can cancel 2 and finally you will get, and here the I1, I2, I3 again, they are also equal in magnitude, so commonly I will call it as IL. That is what IL, and here it is I phase. So finally what is IL? It is root 3 I phase. Now let us draw the vectors. So equal in magnitude, but I am drawing opposite in direction, so that is minus IR. Similarly, I can draw minus IY and minus IB. Now I have got IR as well as minus IB. Here IR is there and this is minus IB, and the resultant vector will be achieved by drawing parallelogram. So this is the resultant vector I1. So that is what line current. Similarly, I can also write I2 is equal to IY minus IR, I3 equal to my IB minus IY. So if I draw the parallelogram for IY and minus IR, I will get I2 like this. Similarly, IB and minus IY, if I draw a parallelogram, I will get I3. So this is how you can draw the vector diagram to know the relationship between the line currents and phase currents. So keeping these basics, let us try to solve one problem. So a three-phase delta connected load is balanced load is given. That means all the three phases will be having same impedance 4 plus j8 ohms, and across which at 400 volt three-phase supply is given. You are asked to find the phase currents and line currents and also power drawn by the load. So let us write the line voltages first. They are, so from the given 400 volts we will write three voltages, 400 at an angle 0, minus 120 and minus 240, and the impedance per phase is given in rectangular form. Convert that into polar form. We have already discussed how to convert rectangular form and polar form using calculators. Now we are interested in finding the phase currents first. So what is phase current? IR is equal to that particular voltage divided by the impedance. So voltage across R phase is 400 at an angle 0 divided by the impedance is, it is common, 8.94 at an angle minus 63.4. So while dividing, divide 400 by 8.94, that will give you 44.74, and take this 63.4 to the numerator. So that is what, minus 63.4, and finally convert this into rectangular form. Similarly, you can also write for IY and IB. The only difference is, so here it is minus 120, here it is minus 240. The denominator is same, and convert all the values into rectangular form. Now after finding phase currents, how to find line currents? We know the formula. The 3 line currents are, first one, I1 is equal to IR minus IB. So subtract IB from IR. And finally convert this value into polar form. Of all your final answer should be in polar form. And then I2 is equal to IY minus IR. Convert that into polar form. I3 will be equal to IB minus IY. Again convert that into polar form. So all the 3 magnitudes will be same, 77.49. Only thing is the angle differs. That is what balanced delta connected load. And then power drawn by the load formula is root 3 VL IL cos phi. So root 3 into 400 into IL is 77.49, and in the impedance we have taken the angle from the impedance, that is 63.4. So that is P equal to 24.04 kilowatts. So I request all of you to go through the videos as many times as you can and get clarified. Thank you.